Hello and welcome to lecture 23 and convex analysis. Topic of today is monotone operators, and for those who attended the convex optimization course, you may as well continue to attend the lectures. So we're going to start with monotone operators, and the first few lectures will be more theoretical, but I think at least in the beginning of the next week we're going to start again with algorithms, which are built on top of over the use of monotone operators. Okay, so I'm not trying to tell you what a monotone operator is in a nutshell yet and why it's interesting. I think we just go forward. I'm going to define this stuff, and then later on we'll see why monotone operators are a great tool when it comes to convex optimization. So topic is monotone operators. So, and one thing to ease notation is from now on I'm going to work in a general finite dimensional Hilbert space. So from now on we're going to denote by X finite dimensional and real Hilbert space. And the norm, or the inner product, will always be denoted by that. And the associated norm would always be just this, and is the square root of the inner product with itself. Of course, our prime example is the standard Rn or Rd with a standard inner product, but there's a little bit more because so all of these spaces are of the form Rd. And the inner product is always then the only possibilities we have for such an inner product for Rd to turn it into a finite dimensional Hilbert space are of the form x transpose times A times Y with A as PD. So, and sometimes we're going to make use of, and later on we're going to make use of this fact that we can have different norms on Rd which turn it into a finite dimensional real Hilbert space. So the main thing for notation is I drop the index of the two norm and, for all the norms. And they're also only going to write x for the space. Okay. So monotone operators. Monotone operators, they appear in convex analysis naturally because there is this operator of the subdifferential. The subdifferential assigns to every point in the domain of a convex function, or in the domain of definition of a convex function, is set, a subset. So if you have a convex function on x, then the subgradient of f at x is a subset of x itself. So actually it's a subset of the dual space, but anyway, it doesn't matter. So we can consider this as a set-valued mapping, right? And so this is what we're going to treat here. So we're going to need set-valued mappings, or set-valued maps. These are usually of the form like A maps X to the set of subsets. So this is the power set, one way to denote the power set. So what does it mean? That means that A of X is a subset of the space capital X. But if I try to sketch a set-valued mapping, it's also actually not that hard. So let's pretend that X is just the real line. So then we can have a real line over here and the real line over there. And then if you fix some point X here, then A of X would be some subset here. And for every point we'll have a subset. So my set-valued operator can look like this. May have a point over here and another square over there, and a line over there. So that will be could be a depiction of a set-valued operator. For every x, you have a subset of x as an image. So this could be one way to depict A. And what you see is that similar to functions, we can identify such a map with its graph, and the graph is a subset of the product space. So identify A with its graph. So the graph will be denoted by dr of A, and is defined by all the tuples x and y in x times x, such that y is an element of A of x. So we identify these two objects. So we note we write so we're going to write x and y is in the graph of A, and interchangeably with y is an element of A of x. And vice versa, every subset of x times x gives rise to a multi-valued operator, or a set-valued map. This is also the same thing, multi-valued operator, set-valued map, okay, same thing. So no matter how you choose any subset here, you can consider this to be a graph of a multi-valued operator. So it sounds pretty boring actually, so why should we need a new name for any subset of the product space? And actually in this generality it's not that helpful. One thing I forgot is, of course, nobody forbid that A of x may be the empty set. So for example, for an x which lies here, this intersection here, this line is empty, so at this point A of x will be the empty set. That's also allowed, which we also know for the subdifferential actually, right? Okay, so now come to the definition. It's not 4, it's 23.1. So the definition says a set-valued map. So we denote it by A maps x like this with two arrows, so there may be multiple images. So is characterized by its graph of A. We've seen that before. This is the definition that is up there. Subset of x times x. So when you write this, you already have this. The domain of A is also written as DOM, like for convex functions. But now we say this is all the x's in the base space X such that A of x is not empty. Okay, and then we can do multiple things with a set-valued map. For example, we can simply talk about the inverse. The inverse of A is defined by its graph. The graph, so the inverse is denoted as usual by A to the minus 1, and this is then defined as, these are all the tuples y and x in the product space, such that y is in A of x. So in other words, we could also say x is in A to the minus 1 of y if and only if y is in A of x. And just what does that mean graphically? For the graph, you just flip the graph, right? You just flip the graph on the along the diagonal, and then you get the graph of the inverse, just like you know from standard functions. Okay, and then we have algebraic operations which we can do with set-valued map as well. So if A and B are set-valued maps, then we can add them together and saying that this A plus B of x is defined of A of x plus B of x, and now here on the right hand side we have the Minkowski sum. So this means like these are all the vectors y plus y star, y prime, such that y is in A of x and y prime is in B of x. So that's simply the set-valued map. The Minkowski sum, same for multiples. Alpha x is, again with Minkowski multiplication, is the set of all alpha times y for y in A of x. And we can also compose that valued map. So A after, I wanted to write B after A. I find this kind of difficult to imagine, but actually, so of course what one should do is pretty simple. You take the sets B of y, B of y, yeah. So first, you take the sets A of x, You consider all the points in the set Y, and then you just map them with B. So that's just how it is. So for first you apply X to A, then you get a set, and then you apply B to everything which is in that set. So that's basically as simple as that. So that is these are set valued maps. So as I said, in the full generality, they are not that useful because they are just a different notion of saying, well, what is a subset of the product space. But by doing this arithmetic as if it were functions, they got the set of all set values operators gets a little bit more structure. Okay, so but it gets more interesting if we restrict to a certain class of set values maps, and this will be the monotone operators or the monotone maps. Okay, so and I just define it. A set valued map A mapping X. So of course here I always used X and X as domain and range, but of course these spaces can in principle be different. So what we will not use this here. So what I want to define is this is called monotone. If oops, that's not a typo. For all y in A of X and y prime in A of X prime, it holds that y minus y prime times x minus x prime is non-negative. Why is this called monotone? Remember, or maybe have a look at the 1D case. So if x is just r and a single valued, so just a standard function, then this here reads as a of x minus a of x prime multiplied by x minus x prime non-negative. So what does that mean? So it means that if x is larger than x prime, then a of x has to also be larger than a of x prime. So, and if x is smaller than x prime, then a of x has to be smaller than a of x prime. So this means this is increasing. Or non-decreasing. I always say increasing and distinguish this with strictly increasing. So it's a slight misnomer that it's called monotone, because monotone would stand for either the increasing or decreasing. In the context of set valued map, monotone is reserved for the case which is called increasing in the 1D case. And there's no such notion as increasing or decreasing for set valued maps. Okay, probably it's not a bad name, because so increasing would make really just no sense if the space is not ordered in any way. So monotone is maybe it's fine, and also that's the standard notion. Everyone calls it like that. For moreover, we say A is strongly monotone with constant mu. Like this, if A minus mu identity is monotone, and A minus mu identity is just you consider the identity as also a set-valued single-valued map. So single-valued or mapping to singletons, you can multiply by mu, and you can take them multiply by minus mu, and then add these things. So that's just straightforward with what we've done. And similarly, you could also claim that what you need is that in this case where x is y is an a of x, y prime is an a of x prime, that this should be larger than mu times the norm difference or of the x's, not the y's. X minus x prime squared. So that's one. Yes. Okay. Okay, this is strongly monotone. So, but now there's one more important notion, which is not so monotone and strongly monotone. They are important, but another important notion is this so-called maximal monotonicity. So A is called maximal monotone, and I can't make up my mind if I call it maximal monotone or maximally monotone. I don't know. Sometimes I think one sounds better than the other, but then the other day I think the opposite way. I don't know. So maximal monotone, if there is no monotone map with a strictly larger graph. Which means you can order all the monotone operators by graph inclusion. So if you add some points to the graph, so here we had the picture of one set-valued map. Of course, you can add something like this, and then you get a larger monotone map, larger by graph inclusion. Of course, not all operators or set-valued maps are ordered by are comparable by graph inclusion. Some just have different graphs which do not overlap, for example, but some of them are comparable. And the maximal monotone operators are the ones which are kind of maximal with respect to graph ordering by inclusion. Maybe I should expand it a little bit because this notion is important. You could also say, so it's there's no monotone map with strictly larger graph. We can say it in the way, this means like if for all x and y which are not in the graph, there exists x and x prime and y prime in the graph, in the graph of A, such that this inner product x minus x prime, y minus y prime is actually negative. Because if this would not be the case, you could add this point to the graph and would still be monotone. So this is really just expanding that there is no monotone map with strictly larger graph. If there is a point outside the graph which still such that still these inner products would all be non-negative for anything which is in the graph, then you could add this to the graph and monotonicity would be preserved. Okay. Good. Yeah, and I think. Yeah, so let's formulate one lemma which is very useful if you want to show or use maximal monotonicity. A is maximal monotone if and only if it holds that if you have for all y and v in the graph of A, it holds that x minus y times u minus v is non-negative, then it should follow that x and u is also in the graph of A. So the logical structure is a little bit confusing at first. So maximal monotonicity is characterized by an implication, and the implication is whenever this here holds for all things which are in the graph, then the other pair is also in the graph. So this is how one can use maximal monotonicity, because sometimes it guarantees your existence of something. So you can sometimes you pick an x and a u, and you always check that this inequality is fulfilled. Then you know that u is an a of x. So and actually the proof is straightforward, but I find it tedious to explain. But because everything is, once you heard it, it sounds trivial, and before you heard it, maybe it's not clear. So let's start with one implication. Let A be maximal monotone, and assume that v is an a of y, which is this guy here. And assume that that whenever v is an a of y, then x minus y times u minus v is positive. Okay. So then, if then these x, so no, I will not write it the other way. If then u is not in the graph of not an a of x, if u is not an a of x, contradicts the maximality. Okay, because you could add these pair then to the graph, and this shows the one implication. So if a is maximally monotone, this implication has to hold. Otherwise, if it would not hold, you could add something to the graph, and you'll have a larger maximum monotone operator. Now assume for the converse implication. Now assume a is monotone, but not maximally so. Monotone, but not maximally monotone. So then you can enlarge it. Then there exists a bar monotone with graph of A is a subset of the graph of A bar. So that means that there exists something in the graph of the larger one, which is not in the graph of A. Okay, but then if you would have that, since this A bar is still monotone, you would have that x minus y times u minus v is larger or equal to 0 for all y and v in the graph of A, which is a subset of the graph of A bar. Oh, sorry, this was wrong. So we assume that this x and u is in the graph of the larger, but not in the graph of the smaller. And then you will have this here. This will be positive whenever y and v is in the graph of A, because this is also in the graph of A bar. But you have that x and u is not in the graph of A, and this is the contradiction to what you want to show. So this doesn't hold, and this doesn't hold. Okay. So let's come to examples. So of course, maximal monotone operators are difficult to depict in dimension larger than 1. So but in dimension larger than 1, you can do it, and it's also, I think it's fairly illustrative to do so. So let's do one example, and maybe I come up with a few others. Okay. So the sine function. So the sine. So we take, of course, x is r here. The sine function is defined as being -1 for x smaller than 0, being 0 for x equals 0, and being 1 for x positive. And you can consider this as a set-valued map by just putting this into sets. So, and of course, we can depict it here. -1, 1. And here let's do it in green. So this goes here. This point is not there because it's here, and this point is not there, and then it's there. Yeah, and this thing is really a monotone map, because you can check if you take 2 points in the graph, then well, in here it's really monotonicity is really increasing. So if you consider this as x and this as x prime, then x is larger than x prime, and the y corresponding y's are the same, so the inner product is 0, so it's non-negative. But if you move the x prime somewhere to the left, maybe here, then you would have this is larger than that, and 1 is larger than minus 1. You have the multiple of two non-negative numbers, so the product is non-negative. Okay, so it's really an increasing thing, but it's not maximally increasing. Right, so why it's not maximally increasing? Maybe before we come to maximally increasing, of course, you can get other monotone operators, monotone maps, even single-valued, by for putting this dot in the middle somewhere else. You can also put it here, for example, right? It would not change. This thing here is still monotone. So you assign the sign of 0 anything between -1 and 1. So you can put it here, you can also put it there, and even you can make such an interval part of the image, right? Why not? It's possible. It's set valued now, and it's still monotone. And so what is the largest thing you can get? You can even do it like that. You can add the full interval from -1 to 1 to the graph. And then this is maximum monotone. Now you try to add any other point of the plane to the graph, you will notice that this is not monotone anymore. Okay. So it's monotone, not maximally monotone. But the multi-valued sign, which we had as the subgradient of the absolute value, so the multi-valued sign is more or less the same. Here it's again the set -1 if x is negative, but here it's the interval from -1 to 1 if x is 0, and here it's 1 if x is positive. That's here, and this is monotone. This is maximally monotone, or maximum monotone. Okay. So yeah. So okay. Good. Okay. Remember, recall that the sign is actually the subgradient of the absolute value on the real line. And that's not a coincidence that this subgradient of the absolute value gives you a maximally monotone operator. That's not a coincidence. Actually, we can prove that it's always the case. All subgradients are not all subgradients of convex and lower semi-continuous functions are maximal monotone operators. Okay, we come to that in a second, but before we're going to do that, let's prove one proposition about maximal operators. And, okay, so if A is monotone and identity plus A is onto, then A is maximum monotone. So that's one way to get maximal monotonicity. If you can prove that identity plus A is an onto map, then you know that A is maximum monotone. Maybe we should talk about what that means. So the first onto means that for every y you can find some x. Maybe I should write that down here. What does that mean? That means for all y there exists an x such that y is in identity plus A of x. So this is this is kind of surjectivity for set-valued maps. And maybe before we prove it, let's check it here. So this is our A, and now let's try to depict how does identity plus A look like. So let's identity plus A. How does it look like? So for each point in A of x, you have to add x. And this can be accomplished by, so you need to add this function here. And so not Minkowski sum in the plane, but Minkowski sum for each x individually. And if you think about it for a second, you end up that the map looks like this. Here it's going like that. This point is not there. This stays here. This point is not there. And here it goes like that. And the same here, the function goes here with slope 1, this all stays there, and then it goes like this. And you see, so for monotone operators, so you may have infinite slope and zero slope, but never negative slope. This is not allowed. So, but zero slope is okay. But for maximum monotone operators, all these vertical jumps has to be full. So otherwise, if the jump is not full, you could just fill it up, and then the graph gets larger, and monotonicity is preserved. And now you see that this guy here is onto. So if you now take any point here on these axes, what is this point, you can go over, and then you will find something which maps there. If you're going to here, you can find that 0 is going to map there. But this guy is not onto. These points here are not in I plus a for any I plus a of x for any x, because I plus a of 0 is just 0 and not this number here, and any other is larger than 1 or smaller than -1. So it looks like this proposition is true, and it is. So let's prove it. Okay, so we start with a monotone and I plus a onto. So we fix some x and u in the graph of A, such that for all y and v in graph of A, we fix some x and u in x times x, such that for all y and v in the graph, you have that x minus y times u minus v is non-negative. So what we need to show, so our aim is show that xu is also in the graph of A. Then the assertion follows from our previous lemma 23.3. So okay, we just need to show that. Okay, so but now we have I plus A is onto, and that means means there is a y solving the following inclusion. X plus u is an element of identity plus a y. So we take the y, we take the x and u, we add them together, and want to have x plus u is an element of identity plus a y, and this is possible. We can find such a y because I plus a is onto. So, but the right hand side, meaning this is y plus a of y. So what does that mean? So what does so this always, so if you know, we often work with inclusions of that type here. X plus u is an element of some addition of sets, and of course we often just omit parentheses about the singletons here. So this is just a singleton y and the add and so on. You know what I mean. So what does that mean? So hence you have there exists v in A of y such that x plus u is equal y plus v. So that is how you can work with such inclusions, so to get concrete. So if x plus u is in y plus a of y, and a of y is a set, there has to be some element in the set which gives you here equality. So this is what I've written here. But we also have this star. You know that 0 is smaller equal x minus y u minus v, and now let's we can so we can, for example, reformulate it that this is u minus v is actually the same as y minus x. So this guy here is y minus x, so this here is negative x minus y squared. from here, you bring the v over here, the x over there, you get it like that. So you get it the other with the sign the other way around, and you get negative norm, but this is positive or non-negative. This shows you that x has to be equal y. And also if x is equals y, then from here you also get, so x minus y is 0, so u minus v is also 0, and u is equal v as well. So, and thus you get u is in a of x as claimed. Okay, that's how this works. Okay, so monotone operator is maximum monotone if identity plus a is onto. So if you're at identity, then you reach everything. So which means somehow it makes sense, right? If a is monotone, it keeps increasing. Maybe it increases very slow, not slow enough to reach everything which you can reach. But if you add the identity, it goes fast enough to reach everything. This is my impression, so my mental image of this in one dimension, and in higher dimensions I have no idea how to depict that. Okay, but this is how this works. There's one important thing. Actually, this is an if and only if. The other implication also holds. If A is maximum monotone, then identity plus A is onto. That's much more difficult to prove, and we'll prove, but we do it in the next lecture. Okay, so I think it's time for the break, and so unfortunately I ran out of steam and I couldn't collect any more new jokes, so here are a few of the old ones again, but anyway, I hope you just make 2 minutes break and then resume with the rest of the lecture. So see you in 2 minutes. Okay, here we go. So, few more facts, one more fact about monotone operators, and then we come to the relation with the subrings. So first, so maximal monotone operators, they have a relation with convexity. I think I'm not going to prove it, but they also have a certain kind of continuity operator, the continuity property. It goes like this. If A is self-valued map from X to itself and maximal monotone, then its graph is closed, is a closed subset of X times X. This follows just for maximum monotonicity. So what does it mean? I.e. if un is a sequence in A of xn, oh, and I forgot to say, for monotone operators, it's quite usual to omit the parentheses here. In the beginning, this may be confusing because not having parentheses and having the letter A here really reminds you of a linear map or of a matrix. But no, this A here can be non-linear and can even be set valued. But anyway, still this is a standard notation, and it's actually pretty handy to omit these parentheses all times. So no parentheses does not imply linearity or single valuedness. It's still a set valued non-linear operator. But if you have a sequence of UNs in the images of X under A, and you have that xn converges to X and also un converges to U, then you can conclude that U is also in A of X. So there's closeness of the graph, and you know closeness of the graph also from linear operators probably. So if you have ever dealt with unbounded operators, I don't know, in mathematical physics or PDEs, there's also a notion of closed operators, which is the same as saying that the graph of the operator is closed, which means exactly this. If the pre-images converge and the images converge, then the limits is the image. Okay, this follows from maximum monotonicity, but not from monotonicity. Okay, how does that go? You take, let's say, for any y and v in the graph of A, we have that xn minus y times un minus v is non-negative. So this is just monotonicity. So but then if now the xn converge and the un converge, this guy here, the inner product also converges, right? It's continuous in both coordinates simultaneously. So then you also have that x minus y and u minus v is non-negative. Oh, and for people who think about what happens if X is a Hilbert space, a non-finite dimensional Hilbert space, then this is still true if you have strong convergence here, but you see that you can get a little less. It's enough if one of the sequence converges weakly. So xn going weakly to X and un going weakly to u. That's also fine, and the inner product still converges, and the other way around. So in an infinite dimensional Hilbert space, you could say that the graph of A is either weakly strongly closed or strongly weakly closed. It's both. It's not either, it's both. So, and this still holds, holding for all y and v in the graph of A. So, but again, lemma 23.3 implies that then you must have u in A of X as claimed. Simple as that. So that's how you use lemma 23.3, right? That you just from this guy, this inequality holding for all y and v in the graph gets you that. And this was already the full proof. Okay, so now let's come to the proposition which tells us that subgradients are monotone. Proposition 23.7. And I think we still have not enough material for 1.5 hours, but I guess that's fine. So let f of x to our extended be proper and convex, then subgradient is monotone when we consider it as a set-valued map, and this is what we can do. So and if f is additionally lower semi-continuous, then subgradient is maximal monotone. So subgradients are monotone, subgradients of convex functions are monotone, and subgradients of lower semi-continuous convex functions are even maximally monotone. So this sounds like a big result, but actually it's fairly simple to prove. And I guess we already proved that, but I forgot. But it's very simple. If you just start with P being a subgradient of f at x and P prime being a subgradient of f at x prime, then you get these two subgradient inequalities, and this is the subgradient inequality at x, but we plugged in x prime, and you can also do it the other way around. You can write down the subgradient inequality at x prime and plug in x. So, and if you do add these two things, you end up with 0 is larger than, so you get f of x prime plus f of x on both sides. You cancel this right away, and here on the right hand side you can write this as 0 is larger than p minus p prime and x minus x prime, which is exactly what you needed. So because one of these is swapped here. Okay, so and now, so how can we prove that the subgradient of a lower semi-continuous function is maximally monotone? And this is now an interesting take, because it depends on the possibility on the existence of minimizers of some function. So if f is no LSC, then by a theorem which we proved a long time ago, 8.2, this function 1 over 2 y minus x squared plus f of y has a minimizer. Actually, we also have a name for it. The minimizer, we called it prox of f of x. Okay, so we can characterize this minimizer by the subgradient sum rule. So the subgradient sum rule holds f is convex lower semi-continuous, that's fine, and this function here is finite everywhere. So it's continuous everywhere. So it's continuous at every point where f is finite. So subgradient sum rule gives us that this minimizer is characterized by 0 being in the subgradient of this. Subgradient of that is 2 cancelled. It's z minus x plus subgradient f of z. Okay. So that's now an inclusion. We rearrange it as follows. We bring the x to the left-hand side and say this is the same as x being an element of z plus subgradient f of z, which we write as identity plus subgradient of f now, which we can now do because we can now add and subtract set-valued maps. So what this here shows that this inclusion always have a solution. For every x, there exists z which fulfills this inclusion. This has a minimizer. Right? This has a minimizer implies that the z exists. So and hence, identity plus subgradient of f is onto. And this implies, so by what was it, proposition 23.5, this is maximum monotone. Okay, so this is nice, I think. So this maximality really comes from lower semi-continuity. You may just, if you have time, just pause the video and try to figure out what happens if f is not lower semi-continuous, and then show that then the subgradient is actually not maximally monotone, or it doesn't have to be. So come up with an example. So destroy lower semi-continuity by kind of making the function jump up to infinity, have a look at the subgradient, and observe that it's really not maximally monotone, that you can add something to the subgradient and still stay monotone. Okay, good. So if we now know that subgradients are maximally monotone, we can So we can write down that. So the class of convex optimization problems is actually a subclass of a different class of problems, namely the so-called monotone inclusions. So we can now write minimize f of x over x in Rn or Rd, and I say x in x is the same as 0 being the subgradient f of x. So in this here is a convex optimization, and this here is called monotone inclusion. So, but in general, monotone inclusions look like this. In general, these are of this form. 0 is an a of x for monotone a. So, and so, yeah, these are one class of problems. Another class of problems for convex f, find minimum, and here for monotone a, find 0. Of course, you know that minimizing function is the same as finding zeros. In the convex case, it's the same. In the general case, it's necessary that the derivative is 0, but here it's, in the convex case, it's even linear. So, and so this is a problem class of its own, monotone inclusions. So probably, so I defined that here, what a monotone inclusion is. It's that. What we're going to do is we're going to develop algorithms to solve monotone inclusions. And this will then be used, of course, and if we have an algorithm which can solve a monotone inclusion, it also can solve convex optimization problems. We just replace the a by the gradient of f. Okay, that doesn't sound too impressive, because why should you just rename things? The nice thing is that this class is a little larger. So there are monotone operators which are not subgradients. That's one thing. And there are complexer, so there are minimization problems which can be formulated as a monotone inclusion, not only like this, but in different ways. We'll come to that, and actually you know one example already. It's the class of these functions where we, or these problems where we applied Fenchel-Rockefeller duality. Remember that we derived this Fenchel-Rockefeller duality or optimality system there, and if you have a close look at that, you see that this is another monotone inclusion, which is in fact not coming from some subgradient. Probably, I think I'm going to have time in the end of the lecture to talk about that in detail. Okay. Okay. Oh yeah. So actually now here comes an example that without lower semi-continuity you don't have maximality. So it's not written as an example, probably I should have done that, but anyway, if you now consider the function f of x being the indicator of the negative axis, no, that I used the positive axis but 0 excluded, then the subgradient of this guy here is either the set which contains 0 if x is positive, or it's the empty set if x is non-positive. So this is monotone. So let's depict it here. That is the subgradient as well as the function actually. So it's also the subgradient. So it's monotone. That's not no problem, but not maximum monotone. So why not? Of course, you can extend the graph by adding a lot of points, right? So what can we do? Let's do one pink and one red extension. So of course, you can add this point here, but it's still not maximal. You can, for example, extend it like that. Then this is a larger graph, and it's still a monotone map. The other, so you can't extend it down here. This would not work. Then you would not have monotonicity. But you can extend it also like that. So maybe I'll do a blue one as well. You could also extend it like this. If you always go up, that's fine. And though the steepest way you can go up is like that. That's also still, but you have to go up to infinity, right? And here also you have to go up to infinity somewhere, or to the right. Doesn't matter. You can also, you could also go like this here, if you like. But you could also go like that. As long as you increase, everything is fine. and the kind of the steepest where you can increase it like this. These are all extensions of this monotone operator, showing that this is not maximum monotone. These are the extreme ways what you can do. And recall that if the red extension here, this corresponds to a subgradient. Again, these are all subgradients, by the way. And the red one corresponds to the case where you include 0, nothing else. Okay, good. Okay, that was that. One more thing is, so what we just see in the proof, that if we say that Z is the prox of, let's say, let's say now lambda f for lambda non-negative. It's slightly different than the lecture note, but it's fine. Of x, this is, recall that it was defined as the minimizer of 1 over 2 y minus x squared plus lambda f of y. And recall that this was characterized by x being in identity plus subgradient of f at z. And now we recall that we can also invert monotone operators or set valued operators. So this is the same as saying z is now equal to, and it's equal to, it's not element of identity plus 2 to the minus 1 of x. And why do we know it's equal? Because the z is unique. By definition of being the minimizer here, and strong convexity of the objective, the z is unique, so there can only be one element here in this subgradient, in this operator. So recall that this here is not a typo. This is how it is. It's equal. This is unique. Z unique since minimizer of strongly convex function. Okay. Yeah, so with this, it's sometimes very simple to figure out how proximal operators look just in a graphical way. So you figure out how the subgradient looks. This is, for my taste, it's not that difficult graphically. You just consider the slopes and just paint it. Then you can add the identity by just tilting the graph a little bit, not tilting, but adding identity, and then flip the graph, and then you got the prox. Maybe I illustrate this once with an example here. So if our function may look like this here. For example, if this is our f, how does the subgradient of f look like? Okay, so here in this interval we have 0 because the function is constant 0. Here the function has a constant negative slope. It's fairly steep, so probably it looks like this. And over there it has a constant positive slope, so probably it looks like this. And in between we have all the slopes, so actually the graph of the subgradient looks like this. Okay, and if we now add the identity, that's now not that hard. We just add it like this. Here we have this same jump, and here it goes like this. Here it goes like this. We have this jump up here, and it goes like this. So this is identity plus subgradient of f. And so finally, the prox of f. You just have to flip it everything, so you need to find these points and these points and these points over here. So maybe it's like this. So here it's a little more. So it may look like this, and then it goes like this and like that and like this and like that. And these all have slope 1 because there was a slope 0 here, slope 1 over there. And these are all flat, and so the length here of this flat part is the jump here, and it's the amount of the increase of slope at that point. And the length here is the amount of increase of slope at that point. And also it has to go to the origin, so sorry for my bad picture here. Okay, so this is why this set value map thinking is helpful when dealing with with proximal operators, so I'd say that's helpful. So because I find that fairly easy, and it's also not hard to figure out the exact numbers here, right? If you know the slope over there, the slope over there is the number over there, and then you can figure out all the numbers. It's just not difficult. And so then if you know that, it's also not that hard to prove that it really is true. But why should you know it's true, right? Is if you construct a proximal operator in this way, then this will work. This is how it is. Okay, and maybe I show you this one thing. This is not in the lecture notes, and that is that. Oops, where is it? Monotone operators play another important role when it comes to convex optimization, namely as optimality systems for more complicated convex problems. So we can recall Fenchel-Rockefeller duality. So our primary problem was minimize, how did we write that? F of x plus g of ax. Let's assume that strong duality holds. Then this was the same as maximizing over y minus f star of minus a transpose y minus g star of y. And the optimality system we had different ways to write it. I choose this way. We had minus a transpose of y star is an element of the subgradient of f at x star, and a of x star is an element of g of y star. So let's write this in a different way here. So we can write this as 0, 0 is in, and then in the first line I write a transpose y plus subgradient f of x star, also star. And down here we have minus a of x star plus subgradient of g of y star. So now we write this as a block operator. So block monotone operator. If we do that, we would here, so the x star goes in the first component into the subgradient of, I forgot, so here should be a star, I guess, right? This has to be a star and this has to be a star, so the conjugate. So the x has to go into the subgradient of f, and the y goes into a transpose. Down here, the x goes into minus a, and down there, the y star goes into the conjugate, the subgradient of the conjugate. So now this here is a set-valued map on of the type x times y. So this y comes from a different Hilbert space, mapping set-valuedly into x times y. Okay, and in fact it's monotone. It's simple to see that it's monotone because we can decompose it. Let's call this maybe m for the time being. We can write this m as the sum of two things, this guy here plus that guy. Right? This is how it works. And this here is monotone. Even maximally so, because it's basically a subgradient, right? It's the subgradient of the function f of x plus g star of y, right? That's the subgradient of this. And this here is also maximally monotone. If the a is continuous and linear, okay. And that's simple to see. So what you need to show, it's a single linear single-valued operator. So let's call this guy here, I'm running out of, let's call this n for a moment. No, let's call it s for skew symmetric. So this s has the property that s transpose is equal to minus s, right? If you transpose it, you get the negative operator. So now if you consider x y being s of x and y prime being s of x prime, and you check out what is y minus y prime times x minus x prime. So then this is, of course, on the left hand side it's s of x minus x prime times x minus x prime. And you see, because of linearity here, now this s is linear, and then, well, it's not linear here. You can just figure that out, and we could have started with 1 vector x minus x prime anyway, but okay. So this is now the same as, by using the transpose, x minus x prime, s transpose x minus x prime. But s transpose is minus s, so this here is minus x minus x prime s x minus x prime. So now you have that this inner product here is the same as its negative, and this implies that this inner product s x minus x prime times x minus x prime has to be 0, and hence it's non-negative. So maximality follows from continuity. We'll come to that probably in the next lecture. So what I want to say here is that even though this problem is now a little bit more complicated, you can formulate the optimality system as one kind of easy monotone inclusion. And the monotonicity comes from the fact that this block operator here decomposes into the sum of two maximally monotone operators. Okay, I'm not going to topic when the sum of maximally monotone operators is again maximal monotone. It's not always the case, but sometimes, as far as I know, I didn't check, unfortunately. But another thing is that this guy here is not the subgradient of any nice function on x times y. It's not. Maybe you can come up with the proof why it's not. And the reason is that that guy here is not a subgradient. So this is a subgradient, but that's not. Maybe you can figure out why it's not a subgradient. Okay. It's not even a gradient, actually. Okay, so I think that's it for today. Again, 20 minutes early, but why not? It's fine. We covered all the things I would like to cover. So what we're going to do next time, maybe go over what we did today, and then I'm going to say what we're going to do next time. So today, we introduced the notion of set-valued maps. It sounds a little bit too general at first, so you just consider every subset of x times x as a set-valued map. And that's okay, you can do that. But what we do is we identify the map with its graph. Okay, you have this notion of domain, and when we can do all the things we can do with normal functions. We can take the inverse by flipping the graph. We can add two things by adding the images. We can scale, and we can even compose set-valued map. Okay. The important notion here is not the set-valuedness. The set-valuedness is kind of a way of thinking about maps. The important notion is monotonicity, which comes in this flavor here. And note that if I write it like this A is not linear. You cannot write this as A of x minus x prime. And generally you can't. In the last example, a second ago, we could, because this was linear, but here in general it's not. So you always have to consider these tuples in both arguments here. Strong monotonicity is a simple generalization. Maximal monotonicity is a little bit of a, at least for me, it feels like a little bit more subtle concept, meaning that the operator is maximal with respect to graph inclusion. We have this characterization here. Maximum monotonicity can be checked like if you always have these inequalities here, then the other tuple has to be in the graph as well. Because if it wouldn't, you could add it, and then you would have a larger graph. And this is, I always forget this formulation, but it's really, really helpful if you want to prove something or use maximum monotonicity. So we consider the sign, and then we have this one thing which implies maximum monotonicity, namely that I plus the operator is onto, and of course A had needed to be maximum monotone before. So monotone plus ontoness of this operator gives you maximality. The inverse is also true. It's called Minty's theorem. We're going to prove that tomorrow. Graphs of maximal monotone operators are closed. Graphs of monotone operators not necessarily. And subgradients are always monotone. Subgradients of lower semi-continuous functions are always maximally monotone. Okay. And then we have this nice new way of constructing the proximal map by making kind of graphical calculations for one-dimensional functions. Figuring out the subgradient on paper, just adding the identity and then flipping the graph, and then you got the subgradient. And I find this much easier than kind of proving things. If you have a piecewise defined function here and writing down the necessary optimality conditions, it's tedious here and there. I like this much simpler. And then a little bit off topic, so not on topic in what is it? Not in the script. It comes probably later. In the context of Fenchel-Rockefeller duality, you have a nice optimality system, which is in fact a monotone inclusion here, which is not monotone inclusion coming from a simple subgradient. And the catch here is that linear skew-symmetric operators are always maximally monotone if the operator is bounded, but it is on a finite dimensional space. And this was the proof. Okay, that's it for today. So next lecture is tomorrow at 11:30. See you then.